Okay, good. Now, yep, I have it. So I hope you
Good.
have it as well. Okay,
Yeah,
so
we
just
can't see you
presented
yet.
the
So
type.
just Guido, let's wait 1 second. So we can see you and the slides.
Okay, so this is a joint work with Meng, Weng, Wong, and this work was done when I was visiting the CCLO at SMU in Singapore. Okay, now what is, just let me start with what is L4. L4, it draws the domain-specific language designed for the legal domain. It is part of the main project from the CCLO Center at Singapore Management University. And essentially, this language provides some functionalities and features to make the language, let's say, accessible to the legal professional. And the language and the L4, it's meant to have a spreadsheet style interface, and I think Meng presented at last year ProLaLa'. But in so also it has an internal representation language where you internally represent the whatever you present in the spreadsheet, but also it has many functions to export in multiple outputs in multiple languages, in multiple frameworks. And today I'm going to explore one of them. So here, what we do when we consider the very basic representation, internal representation of, let's say, legal provisions are represented as rules, where each rule has an identifier, R in this example, and then you have that each rule, it's an if-then constructions where you have a set of preconditions, propositional, formulas, and then you have a conclusion, which is a formula. Also, you have two possible, let's say, guards. One is restrict, and also you can specify what are the rules restricting the current rule, or also you can have despite, and essentially you can specify what rules are defeated by the current rule. And also we will use pre-R and conc-R as the identifiers for the set of preconditions and the conclusion. And essentially this language has been developed, and also it can output in many different ways. And one issue is, well, what about the semantics? Because you have ways to express exceptions. So what about if we are able to map to existing semantics for modeling exceptions? So what we did, we looked at the defeasibility, and essentially here we mean defeasibility is just as general mechanism to deal with the rules with exceptions. And we decided to implement it in defeasible deontic logic. Well, defeasible deontic logic, it's the logic I've been working on for too long, and we've been used in many projects. I think we have encoded probably 50,000 norms and so on. So it has been tested with model 7 or 8 real piece of legislation and so on, so we know it works. And essentially here, to determine whether something altered, well, we have a kind of recursive procedure, and also to incorporate exceptions, and essentially we can assess a conclusion if it is a fact, or if there is a rules, such that the conclusion is what we want to prove, and then we check for all the rules for the opposite, and we see that they defeasibly all. And also, what we do, we just check whether for all rules for the opposite, and for the rules for the opposite, either the rule is discarded or defeated. Then a rule is discarded if at least one of the antecedent doesn't hold, and then a rule is defeated if it's weaker than applicable rule for the opposite. However, there are different possibilities to implement this general schema. Let us consider an example. So let us consider this example here. So these examples mean to represent a situation where there are two different pieces of evidence. The first suggests that a person is responsible for, let's say, for a misconduct, and the second, that the person is not responsible for the misconduct. However, the two pieces of evidence have equal strength, so essentially there is no mechanism to determine that one overrides the rules are in a legal system with presumption of innocence. So essentially, we have that, well, if you're able to prove that somebody is responsible, then you can form a guilty verdict. However, by default, we have a non-guilty. And also here we can see that rule 3 is restricted, has a restrict, and then the restriction is, well, this rule overrides R4. So essentially, if there is a positive resolution for responsible or not responsible, then we have guilty, and the rule R4 it's defeated. So far, so good. So what about a case where we are not able? So we are not able to conclude responsible, and then essentially we can go for the rule 4, which is default rule to assess not guilty. However, what about if in the legal system we have a couple of additional rules? And the first says, well, in general, if there is a non-guilty verdict, then essentially somebody was wrongly accused, so it's entitled to compensation. But by default, there is no compensation. So this can be represented by rule R5 and R6. And then those two rules, again, are opposite. Now, what about if in this situation, if we have, well, not responsible, we are able to obtain not guilty, and then essentially we have a right for compensation. However, here the two pieces of evidence are the same strength. So essentially, it was not suitable to go for compensation. So what we have to do when we consider the defeasibility, we have to consider different forms. One where you can propagate ambiguity and one where you can avoid. And then this feature, it's provided in defeasible deontic logic. So what we do next is just to see how to do on, and then we can concentrate in the few minutes left in what is the contribution, and then you can check in the paper. There is a link in the program. Now, in the paper, we just give a quick description of how to encode defeasible deontic logic in answer set programming. And then this encoding, it's based on a meta-programming approach. So essentially, we don't encode directly in answer set programming, but we use answer set programming as a programming language. And essentially, we just encode the concept of defeasibility, proposition, etc., as additional predicates. And then it's based on the approach I worked on, well, last millennia and about 20 years ago for the extension of the defeasibility. The second contribution is, well, how to encode, how to map L4 rules into the ASP program. And I just give a quick overview of those two. Well, here you can see very quickly there is no need to go into the details here. And again, you can check, and we check in the paper, and you can check the explanation there. And essentially, you can see that the very basic condition is just given by about 10 clauses in answer set programming. And hopefully, if you have time to look at the conditions, you can see they're reasonably self-explanatory. There are another probably 10 additional clauses to handle the deontic part. But essentially, when you have those two, what you can do, you can use support and beaten, and essentially you can define both the ambiguity blocking and the ambiguity propagation version. Well, the final step is just to see how to map our L4 rules. And essentially here, we just take a rule, and essentially we based on the elements we have and the type of conclusions we have, either we go on prescriptive or permissive rules if the conclusion has a deontic nature, or we go for a constitutive rule, so if it's a definition. And then essentially what we do for each element in the antecedent, we just create the element, we specify whether they're defeasible, provable or not, and eventually the type they have plus the support for the superiority. And essentially we just show that it works. Okay, so I think I'm at the end of my presentation. I'm able to take some questions.
Thank you very much.